Hi, everyone. Today we are going to talk about compounding interest. So an interest rate is just a price that borrowers pay lenders as the cost of borrowing that money. So sometimes interest rates are good for you. If you have money in a bank account, the bank will pay you interest for the pleasure of borrowing your money. When they keep your money in the bank, they'll spend it and invest it and make money off of that. So sometimes interest is good for you. You will gain interest if you have money in a savings account at a bank. Sometimes interest is bad for you if you're the person borrowing the money. So if you need to borrow some money to buy a house or a car or something else, then you're going to have to pay the bank extra money for the pleasure of borrowing that money from them. Most of the interest we are going to look at today is the interest that's good for you. So it's something where you have invested money and you are getting more interest on top of that money that you have invested. So we have a formula for calculating compound interest. It doesn't look like it, but it's actually an exponential growth formula. So the letters are different, but if you look closely, you can still see the 1 and the plus. That was a part of our exponential growth equation from the last lesson. So this is an exponential growth equation. It just has a lot more pieces to it. So the pieces are the constants. Okay, so these are values that we're going to fill in based on the equation that's given or the problem that's given. P is what's called the principal amount. That's the initial amount that you are investing. R is your interest rate. And just like we did with exponential growth or decay, that interest rate will be written as a decimal, not as a percentage. N is the number of times that interest is compounded per year. Sometimes interest is compounded annually. In that case, N would be 1, compounded 1 time per year. Sometimes interest is compounded daily. That means N would be 365. So you will have to be told exactly how many times per year that interest is compounded. The variables that are a part of our equation are time, measured in years, and the output is future value. So that is the future value of your savings account or your investment. That's what it will be later after all the interest has been gathered. So let's take a look at an example. So Joyce is just depositing $700 into an account that pays 8% interest compounding annually. So the first thing we need to do is write an equation that gives the amount of money Joyce has in her account at any time. So we're looking to write our equation for that future value. So we need to identify all of the constants that are a part of our equation. So we need our principal amount, which is our initial amount. So that is $700. We need our interest rate, which is 8%, which we will write as 0.08 for our R value. And then we need to know how many times that interest is compounded each year. So annually means once per year. So N is 1. So our equation should read A equals, that's our future value, 700 times 1 plus 0.08 over 1. And then our exponent is N times time, so that's 1 times T. So notice I haven't plugged in any numbers for our variables yet. For T or A, we may do that later. From here, I'd like to know how much money she will have in 5 years. So I want to know the future value of the account in 5 years. So what I have is a time. I know that T is 5. So I'm going to take that time and I'm going to plug it in for the T value in my equation. So we have A equals 700, 1 plus 0.08 over 1 to the power of 1 times 5. Okay, so I could do some simplifying in here if I wanted to, but if I notice I have absolutely no variables on this right side of the equation. I just have all numbers. So I just need to simplify that. If I only have numbers and no variables, I don't need a graphing calculator. I just need a regular scientific calculator, and I'm going to plug those numbers in. All right, so let's go to our Desmos graphing calculator and let's plug those numbers in. So we have 700 and then 1 plus 0.08 over 1 raised to the 1 times 5. So you'll notice if you do 1 times 5, it'll lose the 5 from the exponent. If you notice that, you can either do 1 times 5 in your head, which is 5, and leave it at that, or you can do a little parentheses in the exponent to group that together. And the answers are over here. So $1,028, and we're going to round that to 2 decimal places because this is a money question. So 2 decimal places would be appropriate. So 2 decimal places would round to 0.53. All right, so we know that our future value is $1,028.53. All right, let's take a look at another example. So Eric is going to invest $6,000 in an account that earns 2.6% interest compounded monthly. So again, we need to come up with our constant. So we need our P value, which is 6,000. That's our initial amount. Our interest rate, okay, again, this needs to be in decimal form. So if you forget, you can always divide by 100 to get your decimal form. That is 0.026. And compounded monthly tells us how many times that will need to be compounded each year. So monthly would be 12 times per year. So I'm going to write my equation with those constants filled in. And then my exponent is 12 times t. So in this question, we're asked to approximate how many years it will take to reach 18,000. So in this case, we're giving the future value of that account. We want the A value to be 18,000, and we're going to have to solve for t. So the equation that we're going to set up looks like 18,000 equals 6,000, 1 plus 0.026, 12 times 12t. So this is a different situation than the previous example. If we look, we have a variable on this side. There's a t there. So I can't just type that in. I have to actually use a graphing calculator to help me solve that. Okay, so this is a different situation than the last example. We have a variable on this side, so I can't just type this into a scientific calculator. I have to use a graphing calculator to help. So my plan is to type this into one equation as y equals 18,000, and then this into another equation as y equals 6,000, 1 plus 0.026 over 12 to the 12x. We'll just use x and y for our variables in our Desmos graphing calculator. So again, we're going to have 2 equations that we're going to type in. Y equals 18,000 and then also the right side of the equation. Our goal is to find where they meet. All right, so we will type in y equals 18,000, and the other side of our equation and we'll raise that to the 12x. Right, so our goal is to find where they intersect. Now, I can't see anything. I don't see the graph. I don't see an intersection point. And that's because this y value is so large. 18,000 is what this y value is. That's what we're trying to reach. And I only see up to 6. So I'm going to have to go much farther to be able to see 18,000. Okay, so you'll start seeing that increasing exponential graph. And my goal is to find when it hits 18,000. So I might have to search a little bit. And I should see that straight line across at 18,000. So my goal is to see where they meet. So these two graphs meet at the coordinate point 42.3, comma 18,000. And that's what I'm going to write on here. Oops. So our coordinate point is 42.3, comma 18,000. So we expected the 18,000. That's what we're trying to get to. The 42.3 is our answer. It will take 42.3 years to reach 18,000. So Eric is going to be a lot older when he finally reaches his goal of $18,000. Okay, so let's take a look at a different situation where our interest isn't compounded every year or every day. It's actually compounded continuously. So at every single moment that interest is being compounded. It's a little bit of a strange thing to think about. And it doesn't allow us to use the same equation that we used before. Because if we're going to be compounding every single moment, it's really hard to figure out how many times per year that would be. It's almost like an infinite number of times per year. So we're going to use a different equation for compounding continuously. Some of the constants are the same, and there's one new one in here. So the first constant is the same, the initial amount, that principal amount. And the interest rate is also the same. But notice how the interest rate is in the exponent instead of in the parentheses like before. We also have this other letter here, E. Okay, now E won't change depending on your problem. E will always be about 2.718. E is a special number in math. It's an irrational number. If you remember back in geometry, you had a special irrational number called pi. This is kind of the algebra 2 version of pi. It is a special irrational number that shows up in our equation here. The variables are the same. T is time and A is future value. So you may see an equation or a problem that looks like this. So now we are talking about compounding continuously. So Brooke is investing $300 in an account with 4% annual interest compounded continuously. So let's write down our constant terms. Our initial amount is $300. Our rate is 4%, so 0.04. And now we're compounding continuously. So I don't have a number of times per year. I have a new equation I need to use. 300 is our principal. E is that special number. It's about 2.7, but I'm going to leave this as an E. And then our exponent will be 0.04 times time. So if we want to know how much money she will have after 4 years, that means our time is 4. So when I plug in 4, this is going to take just a plain old scientific calculator to solve because there are no variables on this side. 300 is plugged in. I know what E is. It's about 2.7. And those are both numbers. So as long as I have no variables on this side, we can just use a regular scientific calculator. So let's plug into our scientific calculator. 300. Okay, now if you use Desmos, E is a button that's programmed in this calculator. So you don't have to know that it's about 2.7. You can just write the letter E and it knows that. And then an exponent of 0.04 times 4. I put that exponent in parentheses just to make sure both exponents stayed up there in the exponent. Both numbers stayed up there in the exponent. So this comes out to be about $352, and we'll round to 2 decimal places. So 352.05. So this is $352.05. That's how much Brooke will have in 4 years. Now we want to approximate the number of years until Brooke has 1,000 in her account. So we're going to go back to our original equation, and we're going to say we want our future value to be 1,000. So we will write 1,000 equals 300 e to the 0.04 t. So I'm going to use t again. I don't want to use 4. This is a separate problem. I already finished that problem that dealt with 4 years. So I'm going to leave this as t and figure out what t is. Now this side now has a variable. T is there. So we are going to have to use a graphing calculator. So we'll do the same thing we did on the last page. We will plug one side into one line and the other side into the other line, and we will find where they intersect. So we want to know where 1,000 intersects with our equation. Okay, now again, 1,000 is pretty far up there, and I can only see up to 6. So I'm probably going to have to zoom out and then maybe drag a little to get up to 1,000. There it is. So we see an intersection point of about 30.1 if we were to round. So that's what I'm going to write down, 30.1. comma 1,000. So we expected the 1,000. That's what we were trying to get to. It's the 30.1 that's our answer. In 30.1 years, Brooke will have $1,000 in her account. So she's going to have to wait a little while to get to $1,000. Okay, let's do one more example that's a little bit different. Luna is investing some money into an account. So we don't know how much money she is investing into this account. So we don't know her principal. She wants to have $5,000 after 10 years. So she wants her future value to be $5,000 after 10 years. The account compounds interest daily. Okay, so in this case, we need our first equation, and we need n to be 365. Finally, her rate is 0.015. So we want to know how much should that initial investment be to make this happen. So let's remember our original equation. And let's plug in what we know. Future value is 5,000. The principal we don't know. The rate is 0.015. The number of times per year is 365, as long as we're not in a leap year. And then the time is 10. So we're going to plug this into a graphing calculator. That's because when I look over here, I do have a variable. So I'm going to need a graphing calculator for this. So we're going to plug this into one line and then 5,000 into the other line. Now, when I plug the right side into the graphing calculator, I need to make sure to use variables of x instead of whatever's given. So we were changing t to x. In this case, we will change p to x. Our graphing calculator only really likes x for a variable. Okay, so we will type those two things into our graphing calculator and we will find the intersection point. So our first equation was y equals 5,000. Our second equation was y equals x. Okay, and then just remember that you may need to, get rid of that guy. You may need to use parentheses around the exponent. You'll notice that if you don't, it doesn't understand that the 10 is also supposed to be in the exponent. So I'm just going to do a quick exponent around those two. Okay, now this looks different. It's actually a line, not an exponential graph, but I still want to find where it meets 5,000. And I'm only at 15. Okay, so we'll have to zoom out again and make sure we can get all the way up to 5,000. And there's our intersection point. So our intersection point is about 4,303.55 cents. So when we write that down, $4,303.55, 5,000. So this was our coordinate point. And again, the 5,000 was expected. That's what I was trying to get to. This is the solution to our equation. Now, in this case, it's not a time. It's actually an initial amount. Remember, our variable was the initial amount. So this is our P. So it looks like Luna should invest $4,303.55 if she expects to eventually hit that 5,000 mark in 10 years.